Hello people, so this video will explain how to find the nth term for a geometric sequence, and a geometric sequence is one in which you find the next term by multiplying or dividing by the same amount each time. And the general rule for finding the specific rule for a sequence is AR to the power n minus 1. Take note, a is multiplied by r, and r alone is raised to the power n minus 1. Now this a is the first term of the sequence, and this r is the common multiplier, that same amount that you multiply with every time you move from one term to the next in the sequence. So looking at our first example, our numbers in the sequence are 2, 6, 18, 54. So finding the rule for the term to help us find any term in the sequence. For example, if they ask us to find the 1000 term, we don't have to multiply by 3, by 3, by 3, by 3, by 3 every time to get to the 1000 term, but we can simply use the rule to help us get to the 1000 term in a short time. So general formula, a r to the power n minus 1. A is the first term of the sequence, which is 2, and 3. R here is the common multiplier, times 3, so 2 times 3, and 3 is raised to the power n minus 1. That's it. Our n term rule for this particular sequence is 2 times 3 to the power n minus 1. Now here's the second one. Root 3, 3, 3 root 3, and 9. Now, if you have forgotten your square roots and square numbers, then you wouldn't have noticed the pattern from the first term to the second term here. But from the second term to the third term, you see there's a 3 before, and now we have a 3 root 3. That's 3 times root 3. So the common multiplier, the number that you multiply by 3 to get to a 3 root 3, is root 3, square root of 3. Okay, so root 3 times root 3 is 3 times 3 under the root sign, which is 9, and square root of 9 is a root, square root of 9 is a 3. And from here to here, 3 root 3, okay, I'll show it to you on another sheet of paper here. From root 3, I said the common multiplier is root 3, so let's confirm. Root 3 times root 3, if you remember your surds in grade 9, this means square root of 3 times 3, which is the same as square root of 9, because 3 times 3 is 9, and square root of 9 is a 3. So there you go. From square root of 3 to 3, we have multiplied by a root 3. And from 3 to root 3, we multiply 3 times root 3. Okay, so root 3 is the common multiplier, so we substitute that in place of r, and we have root 3 times root 3 to the power n minus 1. Now, take note, root 3 and root 3 are same basis and they are multiplying, so the rule for indices say when you have same basis multiplying, you add the powers. Now, root 3 here didn't have a power before, but anything and everything always has a hidden power of 1. So putting the power of 1 there, then we write down the same base and we add the powers up 1 plus n minus 1, and we simplify the powers. 1 minus 1 is a 0, leaving us with n. So our final n-term rule for this sequence is square root of 3 raised to the power of n. So here's another fractional sequence which is geometric in nature, where you multiply, or in this case you are multiplying, not dividing, by the same amount to get from one term to the next. Like we did with the arithmetic sequences, we separate the numerators from the denominators and we find their n-term rules separately. Then we combine them as a fraction. So here are the numerators: 5, 15, 45, and 135, so forth. See, from 5 to 15 we have multiplied by 3, and from 15 to 45 we multiplied by 3, etc. So substituting the first term and the common multiplier into our general formula for geometric sequences, we have 5 times 3 to the power n minus 1, and this is it. We cannot simplify any further because 5 and 3 are not same bases. Now we do the same for the denominators. From 2 to 14 we have multiplied by 7. From 14 to 98 we have multiplied by 7, and the same here. So substituting a for 2, which is the first term, and r for 7, which is the common multiplier. Here is our n-term rule for the denominators: 2 times 7 to the power n minus 1. So our rule for the whole fractional geometric sequence is 5 times 3 to the power n minus 1 for the numerators, divided by 2 times 7 to the power n minus 1 for the denominators. Here's another one: 2 over 9, 4 over 27, blah blah blah. Our numerators are 2, 4, 8, 16. Substituting into our general rule, 2 is the first term and the common multiplier is 2. So 2 times 2 to the power n minus 1. Now take note, 2 and 2 are same bases, so we can add their powers up. So since 2 has a hidden power of 1, we write it there, and now we add the powers. 1, write the common base down, 2, and add the powers. 1 plus n minus 1, and collecting like terms in the powers. 1 minus 1 is 0, so we have 2 to the power n. For the denominators, from 9 to 27 we multiply by 3, from 27 to 81 by 3, so our common multiplier is times 3, and our first term is a 9, so substitute in a for 9 and r for 3. Our rule looks like this: 9 times 3 to the power n minus 1. Now 9 can be written as a product of its prime factors. In other words, you can write 9 with a base of 3 to match this base. So in order to simplify it down, and so 9 is the same as 3 squared. So 3 squared times 3 to the power n minus 1. Now we have two same bases multiplying. So write the common base down and we add the powers. 2 plus n minus 1. And collecting like terms, 2 minus 1 is 1. So we have 3 to the power 1 plus n. And we combine these two, numerator and denominator n terms, to come up with the n term for the whole geometric fractional sequence. And here we have it, 2 to the power n over 3 to the power 1 plus n. And you can always prove all your rules by checking if these rules work for the terms that are already there in the sequence. Let's see. So we see our rule is 2 to the power n, 2 to the power n over 3 to the power 1 plus n. Okay, confirming. Let's say we confirm with the second term of the sequence. For the second term, the position n is equals to 2. So we substitute n for 2 into our formula and check if it will indeed be equal to 4 over 27. Okay, it must be equal to 4 over 27, then the rule will be correct. Okay, so let's find out. So 2 to the power n, we are looking for the second term, so n is 2 over 3 to the power 1 plus n is 2. This is equals to 2 squared is 4, and 3 to the power 1 plus 2 is 3. Which is 4 over 3 cubed means 3 times 3 times 3. 3 times 3 is 9, and 9 times 3 is 27. And our second term is indeed 4 over 27. That means our n term rule here is the correct one. Thank you for watching. Please like and subscribe, and see you in the next one.